Today I'll be talking about Pixeltable, a new project, open source, Python native, and data infrastructure for multimodal AI. So this work was sort of motivated by, a few years ago, my interactions with computer vision engineers this was before the release of ChatGPT, who were talking about their work process and how extremely manual it was and how extremely data intensive and time consuming that was. And so specifically, they were dealing with a lot of multimodal data, image data, videos, etc., and spent a lot of their development time on just data storage, data transformations, indexing, etc. A lot of things that had nothing to do with the applications and the algorithms that they worked on. And I believe the same is true today. So if you're building multimodal AI data applications, you'll still be doing all of these things. You have to, when you do data set curation, you have to track changes and track data lineage. You often have scaling issues when you're running in production at scale. Doing model inference is expensive. And also, typically, there is a break between doing development and prototyping and then running a system in production. And a lot of that break comes from the data infrastructure that you will be using. And when you think about that in a wider context, when you're developing a web app, nobody would think of developing it on, let's say, BigQuery, and then in production recoding it against Snowflake, right? That just doesn't happen. But in the AI world, the recoding effort is constant and fairly extensive. So to that end, Pixeltable is meant to address all of that. So it is a system that unifies data storage, data retrieval, and orchestration. And so the purpose of it is to serve ML engineers, data scientists, basically people who build AI data products. And the goal, the ambition is really to cover all aspects of data and orchestration that you need as part of that development process, all the way from experimentation to serving. And specifically, what we want is for engineers not to have to spend any time on engineering data plumbing as part of their application. So there are a few. Pixeltable, in my mind, is novel because it is not a database system. Database systems deal with data storage and retrieval. It is also not just an orchestration system because orchestration systems simply execute, and then storage is often seen as part of an orchestration problem. Here, Pixeltable unifies that by placing both data and transformation logic into a table, underneath a table API. All data interactions are declarative, and Pixeltable is completely unopinionated on algorithms, models, best practices, all of that. So there's no sandbox here. We don't give you an agent framework, things like that. These are all things that are part of the algorithms, part of the value add of your product. And so Pixeltable doesn't take any opinion on those, just like a regular relational database system wouldn't restrict what you can put into your tables, right? So it's really, the goal here is to free you from all data plumbing work and give you complete freedom over the algorithms and how you want to design your products. Pixeltable is Python native. It is open source. You can pip install it and run it locally. There is also, and with an Apache license in particular, which is important. And we're also working on a cloud service, the details of which I'll be sharing shortly, and which will also be available for public release in a few weeks, hopefully. So for the rest of the talk, I'll be going over the functional aspects of Pixeltable, starting with storage, retrieval, and so forth, that that I'm trying to outline here and where I'm trying to say this should cover everything you would ever need to do with data in your application. When you're installing Pixeltable, you are getting a local runtime that uses Postgres under the covers for structured storage. So Pixeltable is persistent. Pixeltable functions like a database system. It uses, like I said, Postgres for structured storage. It uses pgvector for vector indexing. It uses local files for materialization of media data when you're doing local transformations. The runtime system itself consists of a catalog, metadata, versioning system with indexing. There is, for execution of both queries and updates, there is a planning component and an asynchronous executor. There's also a cache manager for interacting with external media data. So in Pixeltable, all media data is external. You don't have to upload petabytes of videos into Pixeltable. And there's also a library of integrations with external systems. So again, it gives you complete freedom of what you want to work with. So it doesn't restrict you regarding the external services you want to use. There's a whole bunch built in, but you can also, through an UDF mechanism, through an internal API, you can also complement that with your own custom logic, including your favorite external API services that are not yet covered by the available integrations. Starting with storage, I mentioned Pixeltable is for multimodal applications. So you are basically getting all data in Pixeltable resides in tables. Tables are persistent, tables are transactional, you're getting concurrency, you're basically getting a fully functional database system. But in addition to the standard scalar data types that you're getting out of your regular relational database systems, you're also getting media data, so documents, videos, images, audio, as an example, and ML-specific data types like arrays and JSON. And media data, as I mentioned, is stored externally and cached locally when needed, cached locally and transparently when needed. So on the right-hand side, I'll be illustrating all of these functional aspects with some code snippets to make it more memorable. And so on the right-hand side, we're creating a table that contains, with two columns, one for videos and one for timestamps. And we're then inserting a single row, and you can see that it inserts simply a URL. And when you look at the schema, it contains these two columns with the video and timestamp data types. On the retrieval side, the goal is, again, to make it so that you can express all transformations that you need as part of your application, including things like model invocation or formatting of prompts or image manipulation, as an example, is all expressible in the query language. You're getting the standard set of relational operators. So there's the familiar select, project, join. You're also getting, because in the AI space, JSON is everywhere, so typically annotations are done in JSON, often model output is in JSON, etc. Oftentimes, you need to take one JSON output and then reformat it in some way, extract some pieces of information, and pass it on to the next model invocation as a new dictionary. And all of that is expressible in the Pixeltable expression language with JSON paths and so forth. The way execution is handled is the planner is breaking every query, and also update statements, insert, update, delete, are all broken down into plans that include both a retrieval of structured information from the underlying relational system, in this case locally Postgres. So basically it spits out SQL, gets the structured data, and then complements that with an asynchronous executor for the Python logic that is needed for what else you want to retrieve or transform. And so on the right-hand side in the code snippet, we see a simple retrieval of the videos you inserted into that table we just created in the last 24 hours. So a simple predicate on the timestamp column, and you are getting back both the video and the the local path property of the video. The local path simply expresses the path where it's cached locally. Again, remember, all media data is external. And the video itself is shown and actually playable if you're running this inside a notebook. And so this query is translated entirely into SQL, and there's no Python logic needed in order to execute that. We will see some examples where you have Python logic later. I mentioned in the beginning that Pixeltable unifies storage, data storage, retrieval, and orchestration. Orchestration typically means you need to execute something, you are doing transformations, you're computing things with the data that you have. And so in Pixeltable, this is done through a concept of computed columns. So you can add columns to a table that and give it a computation expression. In this case, on the right-hand side, we have two examples here. We have, first, you want to extract the audio from the video you just put into the table. And as I mentioned, there's a whole host of built-in integrations with local packages, one of which is PyAV. And you can actually get the audio out of your video by calling this extract audio function, UDF. Applying it to the video column and assigning it a new column name called audio, right? So now you create the audio column and told Pixeltable how to compute the audio values in the column. If it runs, when you insert something, it will run it, produce a file, and store that file locally and put the URI of the file into the database. So everything kind of stays inside that system. We are now, and then after we have the audio, we want to run, get the transcript out, and to that end, you're calling the OpenAI transcriptions endpoint and passing in videos.audio, the audio column you just computed, right? So you're basically just stringing together these computations. It's a very simple, in this case, linear sequence. And when you look at the table schema now, you have two computed columns, audio and transcript, with the audio and JSON. The transcript is JSON typed, and Pixeltable knows how to compute it, right? So the important part here is that unlike a pipeline where you need to feed it input data and you get output data and then you need to figure out where to put the output data, here Pixeltable, the runtime system, is able to maintain the table structure automatically and incrementally. So if you add more rows to the videos table, it will run through that DAG and do the audio extraction, and then invoke the transcriptions endpoint. And because it understands the DAG, if you insert a number of rows, it can actually parallelize it, right? So it understands that you can run multiple rows in parallel automatically. If you had multiple, let's say, transformations of the audio column, right? If you wanted to use the audio file in 3 different other computations that didn't depend on anything else, Pixeltable would be able to run these in parallel because it understands the dependency graph of all of the computations that you're putting into your table, right? So it has a very fine-grained view of what is actually happening as part of the orchestration. And again, all of this is done transactionally. Just to go back to, you're still getting database semantics here. When you insert a new row, it runs through the whole DAG. If there's a failure, actually, with computed columns, you can always have failures. You can have a service outage or other exceptions. It actually has properties. Every computed column has a property, error type, and error message. And so if you have to do a bulk insert of 10,000 rows, and 100 of them fail, the whole thing doesn't fail. It simply allows you to see later what actually failed and then take corrective action. So it's able to, it records, this is, again, an important aspect of Pixeltable, that all the data that you produce as part of the orchestration still lands inside the table interface. So if you have exceptions, they're actually visible through the table interface. You'll be able to query them. They simply show up as a property of the computed column. And you can then run a query on it and check, is this not null? And if so, what is the error message, etc. So again, important concept that all of the data produced in Pixeltable still ends up in the table structure and is queryable through the same table API. Whoops. More complex orchestration, we just saw a very simple pipeline, one value after another. Oftentimes you have conditional data flows, then it becomes a little more complicated. So you can have pipelines that only operate on part of the data. A very typical example would be you have a large table with videos, and you want to annotate a few of the frames of those videos and then train your, let's say, object detection model on that, right? So you might want to do something specifically only for the ones that are annotated. Which are annotated? Well, you can simply define that through a query where you would check, is annotation not null, right? And so what you can do is you can create views that with a filter. So in this case, we are creating a view of the videos table where the timestamp is in the morning hours, right? Timestamp hour greater than 6, and what you can see here is less than 12. So basically videos that were recorded in the morning, we now have a view of that. We can treat views like regular tables, so you can still do additional processing steps on those. You can add more computed columns to that view. So in this case, we are adding an expensive external model invocation by calling a text-to-speech model on the transcript text. And now you have a view v1 that has a new computed column speech. And all views are implicitly parent-child joins. So you can see all of the columns of the base table reflected in the view. That simply makes it easier to express additional predicates against metadata that you might have in the base table without having to do an explicit join over and over again. So here we have a more complicated conditional data flow. And the important part is when you define a view like that, it is, again, automatically maintained, incrementally and automatically maintained by Pixeltable if you add more data to the base table. So you can have as many views as you want, and you can have views on top of views, and so you can define fairly complicated processing pipelines that are all maintained automatically and incrementally. And this is advantageous from a convenience perspective, right? You don't have to figure out what you need to rerun. It's also interesting from an observability perspective. You can now look at the schema of this view and see how exactly the data was computed, right? You might have, if you're running an orchestration framework that produces a bunch of files, you might look at the files a week later and ask yourself, how exactly did I compute them? I can see a bunch of audio files, but how exactly were they computed? In this case, all of the computation, like the recipe for producing the data, is reflected in the schema. And the schema is persistent, and you can look at it a week later and still know what happened. Another aspect that is interesting for the multimodal AI case is dealing with objects that are too large for a model and that you have to break down in some form. So typically, documents, when you're doing RAG, you're doing chunking of the documents, right? Because embedding a whole document doesn't give you very interesting, meaningful embeddings. So you break it up into pieces based on sentences or other structural information, and then you do something with the chunks. Or if you're dealing with videos, you often do things on the frames of the videos, not the video itself. And in general, there is a tendency of larger objects to break down into smaller objects that you can then pass on to a model. For instance, in the medical field, medical images are so gigantic, they're often 20K by 20K pixels that are too large for any model, and you often have to tile medical images, right? So this is another example of having to iterate over a component of a larger piece in order to work with the components. And in Pixeltable, you can define this breakdown by using a built-in iterator API. The iterators themselves are, again, user extensible. And so from a database perspective, you would think of that as a table-generating function. So what we're doing here on the right-hand side is creating a view of the sentences of the transcript we just created. And what will happen is that it creates the sentence view will create one row per sentence of the transcript. So after creating the view, we're running a query where we're looking at the sentences. The first two position is a system populated column that starts at 0 and simply enumerates the components. And we're seeing here the first two sentences of that video clip that we got out of from which we got the transcript. And so here's another example where that happens for videos. We're using the built-in frame iterator to create a one row per frame view of the video we just put into the base table. And here you're telling the iterator to run over the video column of the base table. FPS 0 means full frame rate. And we had one video which ended up being almost 1,800 frames, so 30 seconds, 1 minute by 30 frames per second, about 1,800. And here we are also looking at the first two rows of that frame view. And aside from the frames, you're also getting out a bunch of metadata about the frames. And in general, if you implement iterators yourself, you can basically spit out as much metadata as you want. All of the metadata will end up in separate columns. So again, whatever you produce there ends up being queryable and usable by your application. And another very important aspect here is for video, especially the question of prematerialization versus runtime rematerialization. Videos are so highly compressed that expanding the frames or pre-materializing the frame expansion is way too expensive. You would get a factor 20 blow up in terms of storage. And so Pixeltable is able to rerun the frame extraction at runtime. So basically these frames, when you run a query, it uses the underlying PyAV package to re-extract the frames, and so you get scalability, which is what you need for dealing with video. After you put all your data into the system, you often also want to find it. So typically that involves indexing. In the AI space, everybody's talking about vector indexing, very important. But there's, of course, also B-trees, there's full-text search, and so forth. We're not putting a limit on that. Currently, Pixeltable supports embedding indices and B-trees, but we're planning on adding full-text indexing as well. And the important part here is that when you create an index, it is declarative, right? So like in a regular database system, you simply tell the system, please put an index on this column, and then the system will create the index and then maintain it when you do data updates, right? If you add new data, it is reflected in the index. If you delete data, it will also be taken out of the index. For embedding indices, you need to tell it which model you want to use. Again, this simply underlines that Pixeltable is not a sandbox. You can bring any model you want. In this case, Clip is one of the pre-packaged integrations, but you can do whatever you like. You can call external APIs and so forth, right? The only requirement is that this UDF takes an image and is able to produce an array. And by the way, Pixeltable is fully typed. All UDFs have types, and when you run a query or do an insert statement or update statement, all of that is also type checked. So, which is very comforting if you store data persistently. So in this case, you give it the embedding. It will then use Clip both for images and text, meaning that you now see a query here. The query language for doing embedding vector lookups is fully integrated into the query language as a whole. It's not like a separate API and so forth. It is not something that you need to run independently of your other search. You can combine this with a where clause and basically do faceted search directly. So there's no break there. And you can see it's using a string query for an image column. So it's basically understanding that Clip can do both, can be applied to both strings and images. I mentioned earlier that Pixeltable is completely unopinionated regarding the algorithms you run. So in Pixeltable, you have multiple internal APIs to provide user-defined logic. So the most commonly seen one is the user-defined function, a simple function that takes a bunch of inputs and produces one output, right? So this is something that would be applied to a single row. And here on the right-hand side, there's an example of that. So here's and these can be synchronous and asynchronous. So here's a function that uses an external service to get weather information based on latitude and longitude. Bunch of stuff, relatively simple, uses async IO. And then below that, you see an example of how we can use that in a query. We're using the frames table, and you're calling the getWeather UDF now, and passing in a longitude that bakes in the position, which is completely meaningless, obviously, but I just wanted to get an integer and have some arithmetic in there. So basically, Pixeltable is able then to construct the invocations of this UDF given the parameters that you specify in the query. And just like this is a query, you can also use that in a computed column, obviously, right? Everything, every function, every UDF you put in there can be used in any context. And if you use it in a computed column, the metadata is stored persistently, and it will rerun that every time you do data updates. So this is basically one row in, one value out. There's also the aggregate pattern, where you are taking, sum, average, etc. Those are all aggregates we know from relational database systems. There's an interesting one in the multimodal space. Pixeltable comes prepackaged with a make video aggregate, which takes a frame or a sequence of frames and is able to aggregate that into a video, so you can actually compose videos relatively easily. There's also an audio combination, so you can both do audio chunking. If you have to pass audio off to a model, you often cannot give it like an hour of audio or something like that. So we have a splitter that allows you to break up audio into smaller pieces, and likewise you can recombine audio pieces into something larger. So these are examples of user-defined aggregates. There's another interesting one, which is using analytic window functions. And for instance, so basically a pattern where your UDA sees a stream of inputs and then computes one value per input. So for instance, object detection, object tracking algorithms can be modeled as analytic window functions, right? An object tracker sees a sequence of object detection information and then assigns object IDs to all of the detected objects. So it needs to see something in a chronological sequence. So these are basically functions that take a set of inputs and turn it into one input. There's also the opposite pattern where you take one input and then output a table, right? These are the iterators that we saw earlier, basically table generating functions. There's another wrinkle here, which is interesting, which is you can use tables. We saw that you can put processing logic together into a table and basically define a workflow through the table interface. You can also take that workflow and view it as a single UDF. So this basically gives you a hierarchical composition of complex processing pipelines. So here's an example on the right-hand side. I created a simple table that contains 3 columns, image, an angle, and then a computed column called rotated that invokes the rotate function. Pixeltable comes prepackaged with PIL, the Python image library, and so all images, you can use all of the sort of PIL functions against that. So one of them is rotate. So now we have a table called UDF table that contains a rotated column. And you can turn this into a function. You can give it a function veneer and tell it I'm only interested in the return value rotated. And you can then use this table UDF, which has this particular signature. It takes an image, takes the angle, outputs an image, right? So this is basically view a table as I'm giving you input data and it is computing stuff and it's producing output data. And I can now use that inside a query, which I did here. So I'm looking at 2 frames, and I'm using the frame position as the rotation angle. So you can see that frame 0 and frame 90 is basically rotated 90 degrees. So, 3 seconds in, rotated 90 degrees. So basically, this is hierarchical composition along the lines of what you can do with functions in programming languages, right? Functions are an abstraction, and you can use it in other functions and so forth. When you have data, you also want typically versioning. You want versioning when you are training models because you want reproducibility. And you also want versioning because when you're experimenting, sometimes you mess up your data, and it's nice to be able to go back to a previous version. So Pixeltable gives you versioning under the covers. So all updates are versioned. Every schema change or data update is automatically versioned and creates a new version. In Pixeltable, the version history is linear, so it's not like Git where you have branching and so forth. This was chosen deliberately because while it's relatively easy to merge code, but merging data is pretty difficult. And if you just ran a very expensive transformation or computation model invocation, you probably would hate to have to throw that away just because you have a version conflict. So we chose to go with a linear history. Pixeltable also gives you named snapshots. So this is particularly important for when you're doing model training and so forth. You do want to be able to say, I trained on this, and where this is always accessible. On the right-hand side, we see an example. So snapshots are basically exactly like tables. You can query them just like a regular table. And there's also the revert function. So you can basically undo the last change you did. So what we're doing here is we're creating a snapshot of the videos table. Then we're deleting all of the rows of the videos table. We're creating a snapshot of the frames view, and then we're creating all of the rows of the videos table. The frames view is based on the videos table, so that deletion is propagated into the frames view. The snapshot still has almost 1,800 rows. The frames view now has 0 rows, and when you call revert on your last set of changes, the frames view is also restored to what it was before. Pixeltable in the cloud, I mentioned today, Pixeltable, when you install it, you get the local runtime. The local runtime only uses local resources, so there's no scaling beyond your local machine. The cloud service will give you data sharing. So the idea that if you're curating data sets, you want to share that with your collaborators, you will be able to do that through the cloud service. You will be able to create replicas to and from the cloud. The replicas will function just like regular tables. And the replicas will also contain all of the media data that is needed to provide that functionality. So if you have local media data, it'll package it up and replicate that. Of course, if you have external URLs, there's nothing to replicate there. But the idea being that you're getting basically the performance that the original also has. So the late materialization of frames, as an example, will also all be present in the replica. So this is somewhat similar to Git or GitHub, right? I'm creating a repo locally. I can give it a public URL, and my collaborator can then map the public URL onto my local machine and work with that. There will also be cloud execution. So this is for tables that are actually hosted in the cloud, and you will be able to run queries and updates, etc., against it via the local SDK. These tables will simply have a URI that reflects their cloud location, but otherwise will be functionally identical. And of course, the cloud version will not be necessarily limited by running on a single machine, so you get we'll be able to engineer scale out characteristics into that. I will wrap up shortly. Key takeaways. So this was basically a fast-paced tour through the functional aspects of Pixeltable. And to bring it back to the intro, where I said this is meant to address all aspects of AI-enabled data product development. How does it do that? How is it advantageous to current practices, where you often have a sort of breakdown into a multitude of components that store various aspects of your data or give you various pieces of functionality. With Pixeltable, you have a single system for all data storage. So the ambition is you can dump all your data that is needed for your application into it. And of course, structured data, there's media data. We will probably extend that media data in the future. So for robotics, you have things like point clouds, etc., which Pixeltable does not handle today, but would also make sense. And like I said, medical images. Pixeltable wouldn't be able to handle medical images today or satellite images, but there are some interested parties there. You have, very importantly, a single API for all data access. So all data that is produced by Pixeltable ends up being accessible through this tabular API. So tables are familiar. The query language is patterned after relational systems. You have a lot of expressibility with regards to getting things out of JSON structures. And so all of the data, including things like, let's say, performance logs, etc., will be available through the tabular interface. You have a system where observability is built in from the get-go. So observability here is not a separate feature in a separate API. Tables are logs, and so if you structure your processing pipelines through these tables, all of the individual steps are recorded as column values, and you can see them later and do whatever you want with them. And because the system is based on a declarative API, right? You tell it at each step what needs to be computed, and at a very fine-grained level, what these computations look like. You now have a system that has the opportunity to do cost-based optimization and very fine-grained parallelization, right? So we're able to drive external APIs to basically the throughput limit, as we've seen. Like with the asynchronous executor, we've been actually able to max out our OpenAI and Anthropic rate limits. Oh, and by the way, the asynchronous executor also takes into account for these APIs rate limiting info. So it's actually able to interpret your rate limiting headers and then throttle it and, like I said, drive it optimally. Here's how you can get started. For a local install, you can simply pip install it. Like I said, it's free. It doesn't require any sign up or anything like this. There's going to be a cloud version. You can sign up for the preview at pixeltable.com. We have a lot of resources available online. There's a GitHub, obviously. There's a bunch of sample apps that you can use that cover a lot of use cases, especially around video and documents. We're also looking to, I haven't at all talked about the serving side just because that is not ready from an API perspective, but I mentioned that we also want to handle serving. Serving is going to be based on the UDF concept. So the ability to take any UDF, including a table UDF, and then turn that into a serving endpoint. And any serving endpoint also be able to look like an MCP server. We have a proof of concept implementation of an agent framework called Pixel Agent. This is not an agent itself, it's really an agent framework. It's proof of concept because it's meant to be used as a blueprint for you to go and modify, and it's using Pixeltable for all storage, memory, and retrieval and tools and things like that. And there's also PixelBot, which is a sample implementation of a multimodal AI agent, and that you can actually use today at agent.pixeltable.com. So I'll end here. Thank you for attending.